Hello everyone. Today we are going to see a epifluorescence microscope, and in epifluorescence microscope in an inverted microscope frame. This microscope is from Carl Zeiss, and this Zeiss microscope is able to do your wide field imaging in a transmitted light path. It is also able to do your epifluorescence imaging with multiple colors as a fluorophores for fluorescence type of experiments. But a common problem in wide field system is about collecting the out of focus light, which contributes to haziness of your images. How to deal with it is we have an interesting technology called Apotome, and Apotome added into a wide field microscope can actually improve your image quality, remove the out of focus haze informations, and give you a better resolved images. So it is basically improving your quality of images and making your wide field system not only just a wide field system, but also it improves your out of focus to give you a better resolved images which are more meaningful in your research quality. But the question is, how is this Apotome works? So we will understand the technology behind it and how a normal wide field system with a camera based imaging can also be used to improve your image quality. So in case of the Apotome, if I say, is basically a simplified version of structural illumination microscopy. So with the SIM technology, the grids are being placed after the light source, and as the grids are placed, which blocks the light partially, it creates a pattern illumination. This pattern illumination, when they are falling onto your sample plane, it creates a structural illumination pattern which eventually gives phase informations. And when they are rotated or they are shifted at particular angles, they create multiple phase informations for a single plane. These multiple phase informations are put together and generated a better resolved images which a normal wide field microscope is not capable of doing it. And that is where SIM comes with this Apotome technology. Now, when I'm talking of Apotome had evolved over a period of time. The Apotome had different series, and today what we are going to see is Apotome 3. This Apotome 3 comes with multiple grids. These grids are actually defined as which particular objective, the numerical aperture of it, and the lambda of your selection. So the selection of multiple grids are automatic. You have to select a track for a particular fluorophore. There will be a corresponding LED illumination with a lambda specific falling onto your sample, and this grid comes into the light path, creates a pattern illumination. Multiple phase informations are being collected, and when these multiple phase informations are processed with peer reviewed algorithms, you get a better or a way better resolved pattern illuminations, a way better resolved images which will have more meaning and also give you access to samples which had thickness. So the common problem in wide field is, if the sample is not very thin, your light has to pass through a greater volume of the sample, and eventually the emission coming out from different planes of the sample will also get collected, because there is no mechanism of like a pinhole or any other physical part which actually removes the out of focus signal and only collects the in focus signal, as in case of a confocal. But in this case, the grid does the job. So with the grid in the light path, it will only form a sharp grid pattern at the plane of focus. And once it forms a sharp grid pattern, because of multiple phase informations taken for a single plane, that will only be processed, and your out of focus blurry grid positions, Z positions, will be eventually removed, and you will be left with only with signal and minimal noise, thereby giving you an image which is more or less like a confocal type with a better resolution in XY versus Z. As this process is very simple, it can be upgraded on your existing wide field. So For people who had challenges in tissues, in thick samples, in volume samples like organoids, or you had scaffolds where your background informations are too loud, you have a lot of autofluorescence which eventually contributes to the noise, all that non-important signals which actually are noises can be eventually removed, and you end up getting or collecting signal only from the plane of the focus, which is well resolved in the form of your images. So I'll show you the system now. This is the Axio Observer 7, and Axio Observer 7 is an inverted fluorescence microscope frame, and as you can see, this is the stage. Below the stage you have the objectives here, and the top portion where you have the condenser and you have a transmitted light path. And now this is a micro LED which has been put here because of the compact design and better light output. You have controls of the intensity, and after passing through the condenser, the light goes straight. From here you have come the light, or you can see the sample, focus it through your eyepiece. Now this eyepiece also, you can actually change this angle based on the intraocular distance which you have for better visualization. You also have the Z movement, the coarse as well as the fine focus, both are here depending on the step size. If you're working on lower magnifications, you use a coarse focus. If you're using a higher magnification like 40x or 63x, you should be going for the fine focus. And they are both, like if I am a left-handed or right-handed, both are available on both the sides of the microscope frame for the ease of use. In addition to this, the light source which is given for fluorescence is basically Voluma 7. Now Voluma 7 is a LED based light source. Like it has different lambda specific LEDs put inside. Depending on what fluorophore of my choice, I can switch the LEDs and then focus it onto my, or put it onto my sample. Now I have a touch panel control. If I am not using the monitor or the microscope, I just want to use it to visualization purpose for optimization of my sample, I can use this and control all the motorized part of the microscope frame. Now, how the power is being distributed? For the power, I have the power supply, and this power supply, one power supply box gives power to all the components of the microscope. The second power supply box gives power supply to the motorized XY scan. Now this motorized XY scan, as they are electronically controlled, means I have to give the coordinates in the software and it can do the XY movement on its own, provided the coordinates are being fed. And this is manually also operable. How? With the help of a joystick, and this joystick will help me to move the XY stage in the direction so that my sample is being positioned. To keep the sample, I will be using a stage top accessory like this one. This stage top accessory has basically the grid, and it goes and sits onto the top of the stage. Here I have two sliders which will allow to put my glass slide into the position. So this is, I'm using a standard glass slide which is 75 by 25 mm, and this is one of the sections, larger sections, which I'll be using here. This has lot of background information because it's a thick tissue, and to see how wide field will be giving more background light, or in case of a contributing to the hazy informations, I will be able to remove with Apotome all the hazy informations and collect only the signal. So let's see how it works. But before that, let me put the sample into the position. I will be gliding this accessory, and now it is in position. With XY, I will be actually moving the sample and bring it in the light path. I also am using right now, so in this system, what I have is 5x, 10x, 25x, 40x, 63x and 100x. So all magnification objectives are being given. Out of all this, 25x, 63x and 100x are oil immersion objectives. So for oil immersion objectives, you need to give this basically immersion oil which comes from Zeiss again, and this immersion oil is having a refractive index of 1.518, which is very close to the refractive index of glass. And that is where the deviation of the light path has been taken care of. The light travels from glass to oil to glass without any deviation. So giving me more collection of the light, and that eventually is helpful in reproducing my images onto the system. So this immersion oil is important. We have to add a minimal drop of immersion oil on top of the lens. And right now I'm using a 63x objective. This 63x objective is being used, which has a numerical aperture of 1.4. With a oil immersion it comes, and once I'll put it here and do the focus by giving the light in this segment in the microscope. So now if you can see, this is a blue light which is coming, and your emission will be green here. So I'll be seeing a green color here. So if I try to focus my sample, let's see. Okay. Now once my sample is focused, I can see it in the eyepiece, but then the time comes how to see it in a camera. Basically the detector here is a camera. So the camera here is AXIOCAM 807 mono, which is a 7 megapixel camera. It is a larger chip size of around 17 mm, and if you can see, this has a pixel size of 4.5 micron by 4.5 micron. So it has a high quantum efficiency, roughly around 78%, which is a very good camera where you can collect more number of photons and reproduce in the form of an image. So this is again AXIOCAM 807 mono, is also from Zeiss. So the integration of the camera with the software with the hardware is seamless. And that is where Zeiss comes to a universe of a one-stop solution. Now the focus is more towards giving you a complete solution. It's not the instrument which we will be offering. As future or as we move ahead, we will be having a more complete solution to offer. So till then, this is the system we have been discussing, and in this system the operation part to load the sample and to see it is done. Next, what I'll show you is in the software, and in the software we will see how to, after focusing, how to actually capture images which are of high qualities. So now after I have placed the sample and focus is there, and once the sample is focused, I will be now transferring it to the software, and in the computer I will start using the Zen platform. The software here is Zen 3.12 version, and you can see the Zen 3.12 version is loading. You can see a startup. Once this software is loading, it will be the master controller for all the motorized part and the components of the microscope body. So it has to be opened only after your entire microscope is powered and they are in the right configuration position. Once everything is powered, is there and they're responding, the software should be opened, and the software will start initializing the hardware. And during this process, all the components which are under control, which has a power supply, will revert back to the software, and then you will see an error-free startup. So this is the guest user interface of Zen 3.12. You can see here, this is the 3.12 Zen Pro version, and in this version you will have locate, where I have all the controls of the motorized parts of the microscope. Then I'll go to the acquisition, followed by processing and analysis. So in case of locate, I have different fluorophores which I've already used during the time of focusing. So for example, if I want to see a green, so I will click here, and you can see this is my Viluma light source, which comes with 1, 2, 3, 4 LEDs which are integrated corresponding to blue, or basically the UV excitation, then blue, green and red. So blue, green, red, far red, you can actually acquire in this system depending on what lambdas you are using. So right now for the green, I'm using 469. For DAPI, you will be using 385. For red 555, and for far red it has to be 631 lambda. Now this 631 lambda is only for the far red, and as I keep selecting, you can see the color codings will also come. So UV, blue, green, red, and you can select the corresponding intensity as well, so that what particular intensity is actually going into your sample you can also monitor. Now the interesting part is, being a single lambda specific, I have the entire choice of selecting the lambdas individually or together depending on my sample. So right now if I use only green and I want to see for what color is there, so you see blue light is going, and this is my stage. My objective is 63x 1.4. Emission is happening back. I'm using a filter here called EGFP filter. This is 38HE. So this EGFP filter, in this particular system, I have for EGFP, I have for red, I have for DAPI, and also I have for DIC. A separate filter is already put here. So depending on that, my blue light is going and emission is green, which is collected through the eyepiece. I can also see it live from here, that how this sample is in focus or not. By using the mouse also I can focus it like this with the scroll bar, and then find which is my best plane of focus. If I want to go fast or slow, that option is also here, and then gradually you can see here my sample has come to focus. So once it has come to focus, this is a normal camera microscope. Now if I give it a color which is usually the green, then this looks like a hazy informations because it's a thick tissue, and you see that there is no clarity or there is no sharpness here. So if I just take one snap, I will get an image like this. But then comes the apotome in the light path. So if you follow the light path, I have the light source. This is the Viluma 7 light source which I'm using here. Intensity is 42%. Then this is the apotome grid which comes into the light path. So apotome grid will come after the light source, followed by the filter, and now it is going to the camera. So in this case, if I see how the grid looks like, let me see how the grid is looking. I'm not able to see here. So once my focus and everything is done, I will go to the acquisition mode and I'll do my acquisition in the best configuration possible. So once I am at acquisition mode, I'll go in the smart setup, and from here I will select, like I can select one die, I can select two dies. So maybe Alexa Floor 568. So two dies I've selected, and these two dies are being imaged. So once I select these two dies, I'll simply have to say okay, and then you see my two channels are visible now. One is corresponding to green, one is corresponding to red. Usually the higher lambda can be placed on top, so that you start imaging with higher lambda, your chances of bleaching is less. For 568, what will be the LED? The 555 is the LED of the choice. And then comes the camera control, where I will put it as auto exposure. You can also do a shading corrections if you require, but if not required, it's good enough. And then I'll try to see live that how my sample looks like, whether the focus and everything is there or not. And then am I seeing the grid here? So this is the question which I have to ask, whether the grid is visible or not. I can slightly increase and decrease the exposure, auto exposure, because my signal intensity is good. So to have less time in acquisition, I can actually reduce the exposure time of the camera, and then this is how I'm changing the focus slightly. I can also do it from here. Slight focus adjustment has to be taken care of. Yes, I can see the grid. And if you want to see the grid more clearly, let's do it in continuous mode, where my grids will be very much visible. Now you see the lines. There are two colors which are being taken. So I have not adjusted the green, but then we need to adjust the green as well. So green 469 lambda is being used. I'll put an auto exposure for the camera, and then try to see my green intensity is loud. I can reduce my exposure time to less than 100 millisecond. That is also a good number. And then I'll remove the auto correction part in both the cases, and I'll start with taking. But before I go ahead with final acquisition, I have to see whether my Apotome is active. So you see Apotome acquisition is active, tick tick, and I'm using 5 phases information. I can increase this to maximum 15 phase informations and my grid will be visible. So depending on how much resolution you want to push, you can start with 5 phase informations or you can go to maximum to 15 phase informations. And if you want to put a correction, then you can also do a correction, but it has to be a global correction because it is a rolling shutter in the camera. So once this is done, you have made these points, you just have to take a snap. It will be 2 color images being there, 1 and 2 color. And once I have 2 color images, now you see my background information is quite gone. So if I compare the previous snap which I took, you see this was my just camera without Apotome. But now if I take with Apotome and if I remove just 1 color, now you can see the same image, but the background is much less, my intensity is much less. So if I compare side by side with this Apotome image, then I will put along with it this image. Now you see the difference. This is basically my camera image in a wide field setup, and this is my Apotome image which I have put in the light path. And because of this structural illumination pattern, all these haze informations are gone. It is not actually it is not changing the image, it is actually removing the non-specific signal, keeping the signal which is there in the plane of focus. So if you want to remove this, you have to put your Apotome in the light path. And again, if I show you where my Apotome is, my Apotome will be in the light path after the light source. So coming back here, this is my light source, and after that you have the Apotome in the light path, and then comes the filter. If I remove this Apotome, what will happen? I will be doing the same imaging, but then it will be something like this case. So this is the gross difference between a wide field epifluorescence microscope image and a wide field epifluorescence microscope with an Apotome image. This Apotome image can further be processed, and that processing can happen in the processing part where there are a lot of features in addition to the standard Apotome. So if I want to do a Apotome deconvolution, so this image I can further use to sharpen it, right? And for that, what I can do is I can use a normalization. I can set the strength. If my signal here is not that great, I can keep it medium or weak. And if my signal is too loud, I can keep it for strong. So for this case, I'll be keeping it at medium. And then do I need any corrections? Do I need to have a background corrections? Do I need to have a bad pixel corrections? If you want, you can do it. Set in the input, this particular image has come. So now whatever processing will apply on this particular image, and you will have an output. So to check this, what you have to do is, let's see, apply. It will apply a deconvolution algorithm, and after doing a deconvolution algorithm, now you see your image has become little bit more sharper. So all these features which were earlier not very much sharp, now see there were a lot of grainy informations, but here it has become little bit more sharper, and the small signals have started coming. So I must tell you, this sample is a section, and it's an embryo section, which is a very thick tissue, which is very difficult to image. And if you try to image in a wide field system, you will end up getting no specific resolution or no specific anatomical details which your dye is about to give you. But the same image can be drastically improved and worked for better resolved structures by using an Apotome in the light path. So that's it from the Apotome side. This can be done with, as I showed, I have taken only 2 colors because in my sample there are only 2 colors. You can additionally use multiple fluorophores depending on how many LED illuminations you are having and the filters you're using. So in this system, what filters do you have? As I showed you, again, you have separate filters for blue, green, red, and DIC analyzer, polarizer, DIC filter is already there. So these are there. In addition, there is a apotome calibration filter, which is also a part of the turret, filter turret. Rest, you have the camera, which is being redirected from the camera, from the microscope frame side port, and then you start taking images at a faster rate. This is all about multicolor imaging. In addition, if you want to do a Z-stack, you can do fast Z-stack by selecting the Z-stack, and then the standard method where you can give multiple set and so the range, and in that, if I show you the range, I can actually go from one position to other position in this. So this is my one layer. I'm going to the out of focus. This is my set first. So once I say one Z plane, I'll come back to focus and go to the other plane, and I'll say set last. So this sample is roughly 24 micron thick. Now if I follow Nyquist, I can best give 270 nanometer Z step. So if I do 270 nanometer dividing 89 slices, I can acquire. Now here again, your camera exposure plays an important role. Lower is your camera exposure time, faster your acquisition will happen, and then you'll completely know time. So 89 multiplied by 2 will be what we are going to do it. Let's see, we'll do full Z stack per channel, and then we'll start imaging. Now calibration data, because if you want to do calibration, you can do a calibration, but that has to be done with a reference calibration, which if you have given good, or if you have not given, then also you can run the data. Now you can see different Z slices I'll be capturing, and that will be happening over a period of some time. So what it's taking, it is doing number of phase informations per plane. So 89 multiplied by 2, and then multiplied with the number of phase informations which I'm doing. So in this case, it is 5. So practically it is 89 multiplied by 2 multiplied by 5 is what you'll be getting it. So roughly it is 890 different frames it is acquiring, which is pulled together to 89 slices per channel. And that is what we are going to see it. It is going to take 7 minutes. Okay. So we'll just wait for 1 to 2 minutes and we're good to go. So once the acquisition has stopped, go to the processing. In processing, I have taken, like further I can process this as I was doing previously, and then I have been using the deconvolution. This is my input data, and if I say apply, let's see how my apotome processing image comes. Once this processing has been done, then I will move to create a 3D structure where I have taken multiple Z slices, and these Z slices when complete, they will be stacked on each top of each other to form a 3D reconstructed image, which will be giving me a 3D view of this particular tissue section. So as you can see here, this deconvolution processing is happening. As this is a larger file, you still have like it will take some time. The important thing is, whatever system you're using, make sure you have enough RAM, CPU and GPU. You can see the load which runs in the background as and when this processing happens. So this has to be seen, and you have to keep in mind that it's a system load will be high, and it is basically demanding more capability in the form of the CPU, which will be required. So now let's see how it's almost being processed. I can enlarge this window and I can show you this is almost being processed, and just a moment, it will be completed. So almost okay. Yeah. So now once this is done, I have got this frame, and if you can see by moving the Z slices, I can move the Z onto different planes. But here you see 89 Z slices I have acquired. Time to see it in the form of a 2D, and once I see in the form of a 2D, it will process and give me the data in a 2D. Now you see this data looks very clean. All the haze informations are removed, but it is like over, little bit over also. You can slightly make it look smoother because the intensities are too high. So if you try to make it look smoother to some extent, yes, it works. Let's say 0.5, 1 is too much. Your gamma can be slightly adjusted, and now you see here. So the sample which was earlier too thick and you are not able to see that throughout the entire volume because of the out of focus haze informations. Now I have this informations which are quite meaningful. You can see zoom in and I can slightly brighten up. Now you see this is much sharper and I can go to different Z planes to give you much clearer image. So this is the quality of image. If I make it bigger, this is the quality of image you can expect. And that is where your Apotome plays a very important role, because Apotome can transform your wide field image and your journey from here, and it can take you and give a result till here. So this is the same sample, same 63x. I've been using it for the wide field as well as for Apotome, but this is the image difference which I am trying to show you, and hope this makes and gives you an understanding that how if I do a comparison side by side, then this is the comparison which you are going to see. And this is for two colors, this is for one color, and you can see both the images. So with that, if you want to use Apotome 3 here, you will be using Apotome 3 to show you. So this difference is actually done or carried out by this module, which is Apotome 3. I'll take the slider out to show you what is this Apotome 3 module. So this is Apotome 3, this is the slider, and in this you have the grid. This grid comes after the light source, and you will see, if you see closely here inside, they have parallel lines which are put inside, and this slider is automatically controlled with the electronics, so that the grid is selected based on the objective and the lambda on which you are working with. Now this goes in the light path in the f-stop. So at this will go inside. Once it is inside, this Apotome is active. If you want to take the slider out and keep it outside one notch, then Apotome is not in the light path and it becomes an epifluorescence microscope. So it is as easy, like just put it back and you are in Apotome mode, just take it out and you are in normal wide field epifluorescence mode. And that is the magic in the form of the result. And that is the magic between these two. If you see, both the images are very, very different. You are getting almost like a confocal type of image, which is highly resolved and which will give me much better anatomical structures and other informations, well resolved compared to the standard wide field system. So next time, check in your wide field system whether you have an Apotome or not. If you have, good, but if you do not have, you can use this to upgrade your existing epifluorescence microscope from Zeiss and get a confocal like images.